If you've ever glanced at organic chemistry, you've probably seen what looks like a terrifying list of millions of different reactions. But what if I told you it's not about memorizing that list? Instead, think of it like a language with a surprisingly simple grammar. And today, we're going to learn the rules of that language. So that's the big question, right? How can this incredibly vast and complex world of molecules all play by the same small set of rules? That's what we're going to unpack. By the end of this, you'll start to see these really elegant patterns hiding in plain sight.
All right, so here's our game plan. We'll start with the fundamental rules. Then we'll meet the key players that show up when bonds break. After that, we'll walk through the main types of reactions, adding things, removing them, swapping them out, and then get into some major transformations. Finally, we'll put it all together. So let's kick things off with the rules.
To really get a grip on organic reactions, you can't just look at what you start with and what you end with. You have to understand how you get from A to B step by step. And in chemistry, that how has a very specific name.
It's called the reaction mechanism. Honestly, the best way to think about it is like a play-by-play commentary for a sports game. It's not just the final score, it's every single pass, every move, every moment that leads to the outcome. It's the story of what the electrons are doing.
And every single one of these stories, every reaction, starts in the exact same place. A chemical bond has to break. But as we're about to see, not all breaks are created equal. So a bond can split in basically two ways. On one side, you have homolytic fission. Homo means same, so think of this as the fair split. The bond breaks, and each atom walks away with one electron. This creates some really reactive things called free radicals. But then on the other side, you have heterolytic fission. Hetero means different, and this is the unfair split. One atom gets greedy and takes both electrons, becoming negative. The other is left with nothing and becomes positive. This is how you get ions.
And this whole bond-breaking drama, it gives us our main characters on the chemical stage. First, you have the ones that are now poor in electrons. We call them electrophiles, literally electron-loving. They are desperately searching for electrons to fill that void. And then you have the electron-rich ones, called nucleophiles. They're nucleus-loving and have extra electrons that they are just dying to share to form a new bond. Really, a ton of chemistry is just the story of these two finding each other.
So now that we know how bonds break and we've met our key players, let's look at the actual plays they run. We can group most reactions into a few really simple patterns, starting with the big three: adding, removing, and swapping.
First up, the addition reaction. And the name, well, it says it all, doesn't it? You take molecule A and molecule B, they combine, and you end up with just one bigger molecule, C. It's the chemical version of two become one.
So how does this actually work? Well, take a look at ethene here. That double bond between the carbons, that's a spot that is super rich in electrons. It's like a set of doors just waiting to swing open. So when a bromium molecule comes along, those doors pop open, the double bond becomes a single bond, and the two bromium atoms get added right on. It's that simple. Next up, we have the total opposite, the elimination reaction. Here, instead of combining things, we're doing the reverse. We're taking one big molecule and kicking out a smaller piece, which breaks it into two separate things.
Check this out. We start with bromoethane, which has all single bonds. But if we remove a hydrogen from one carbon and a bromine from the other, well, those carbons need to do something to stay stable. So what do? Boom! They form a new bond between them. A double bond appears where there wasn't one before.
So you see the pattern here, right? Addition and elimination are perfect mirror images. An addition reaction takes a double bond and turns it into single bonds. An elimination reaction takes single bonds and creates a double bond. They're just two sides of the same chemical coin.
Okay, our third core reaction is substitution. This one isn't about adding or removing things from the whole molecule. It's just about swapping one part for another. One group leaves and a new one takes its place. It's a simple, direct trade. And here is a fantastic example that brings our star players, the nucleophiles, back into the spotlight. So we have bromoethane, and in comes a hydroxide ion. Remember, that hydroxide is loaded with extra electrons, making it a perfect nucleophile. It sees the carbon atom, attacks it, and kicks the bromide right out, taking its place. That's it. The bromide is substituted by the hydroxide. This is one of the most important reactions in all of organic chemistry.
All right, we've got the basics down. Add, remove, and swap. Now let's level up and look at some even bigger, more transformative reactions, the kind that can fundamentally change what a molecule is, or even build entirely new materials from scratch.
Let's talk about oxidation and reduction. Now, you might have heard some complex definitions for these, but in organic chemistry, we can keep it really simple. Just think of it like this. Oxidation is generally gaining oxygen atoms or losing hydrogen atoms, and reduction? Well, you probably guessed it. It's the exact opposite, losing oxygen or gaining hydrogen. It's really just about keeping track of the O's and H's.
Next up is hydrolysis. Let's just break down the word. Hydro for water and lysis means to split or break. So hydrolysis is literally just using water to split a molecule apart. It's actually a special type of substitution reaction where water itself is the nucleophile doing the attacking. You see this happen everywhere, in the lab and all over the natural world.
And finally, we get to polymerization. This is where chemistry gets truly epic. We're talking about taking tons of small, simple molecules called monomers and linking them together, one after another, to build these enormous, long-chain molecules called polymers. This is how we make everything from plastics to fabrics.
And the idea behind it is so powerful but so simple. You have all these individual units, the monomers, and a reaction just makes them link up, head to tail, over and over and over again, forming this massive repetitive chain. It's kind of like snapping together thousands of Lego bricks to build something huge and completely new.
So, after all that, let's just take a step back and look at the big picture. What's the grand design that all these reactions are a part of?
Well, here they are. These are the 7 fundamental verbs of organic chemistry. Almost any complex, crazy-looking reaction you'll ever encounter is really just some combination of these 7 basic patterns. Add, remove, swap, transform, and build. That's the heart of it.
And that, right there, is the most important takeaway. Please don't try to memorize reactions. That's an impossible task. Instead, learn to recognize the patterns. The moment you can look at a reaction and say, oh, they're just adding something there, or hey, that's just a substitution, you're no longer just memorizing. You're actually starting to speak the language of chemistry.
So, think about it. If these are the verbs, what kind of sentences can you start to see forming all around you? The next time you pick up a plastic bottle or wonder how your food digests or how medicine works, remember these patterns, because chemistry isn't just happening in a lab. It's writing the story of our entire world.